So in the first part of this video lecture, we saw Borel Cantelli lemma, two of them, Borel Cantelli lemma 1 and Borel Cantelli lemma 2, and we saw that when the measure of certain sequence of events is summable, then the measure of the event that infinitely many of them occur is 0. And if we combine this with the last proposition of the previous video lecture, if the event is this event here, this means Fn converges to F mu almost everywhere. So we start today's video lecture exactly with this remark. The remark saying in practice, what we want to do is we want to apply Borel Cantelli lemma 1 to deduce almost everywhere convergence. And to do that, what we can do is we prove that for every epsilon, this series here converges. And then we can apply Borel Cantelli to conclude that this event here indexed by n will not occur infinitely often. Almost surely they will not occur infinitely often. And that means exactly that Fn converges to F almost everywhere. So here's an example of random variables that will converge almost surely to 0. And it's not an explicit example as in the previous video lecture. Now we really need to resort to Borel Cantelli in order to approach it, because we don't have an explicit construction of omega giving us Fn by a formula. Instead, what we have is there's a probability space. We assume there exists a probability space. I'm not describing it explicitly, on which it is possible to define a sequence of infinitely many independent random variables, each one of them with distribution uniform on 0, 1. Okay, so what is this probability space? It's a probability space where it's possible to define ta, 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 just a bunch of uniform variables arriving all the time on this interval from 0 to 1. So we have these infinitely many arrivals of points in this interval between 0 and 1. They are independent. And now we consider yn to be the smallest among the first terms in this sequence. So here is my yn. It's just the smallest of all of them. Okay, so well, intuitively, it's clear that as we increase n, the chances are that we're going to get more and more points here. So we're getting points everywhere, but well, at some point we get one more here, and at some point we're getting one more here. So that if we make it a bit more clean, you'll get 1 point here, and then we get points all over the place, and then at some point one more point here, and then points all over the place, eventually one more point here. So we keep getting one more point, one more point, one more point. And what this example is saying is, well, indeed, this yn will converge to 0 as n tends to infinity. And how can we prove that? Well, we want to prove that using the previous remark. So we want to show what is the probability that yn is larger than epsilon, and we want to show this is summable. Well, probability that yn is larger than epsilon, this means exactly how can the minimum of n random variables, independent one, be larger than epsilon? Well, this is the probability that x1 is larger than epsilon. Well, let me remove the absolute value. They are all uniform anyway, on 0, 1, so they are all non-negative. x1 is larger than epsilon. x2 is larger than epsilon. Xn is larger than epsilon. Well, this, by independence, this will factorize. This will become x1 larger than epsilon, x2 larger than epsilon, times the probability that xn is larger than epsilon. And since now they all have the same distribution, they are all uniformly distributed, so this becomes the same as the probability that x1 is larger than epsilon. Well, we know what that is. That is 1 minus epsilon. And this other one is also 1 minus epsilon, 1 minus epsilon. So this will be 1 minus epsilon to the n. This will be this probability. For each epsilon fixed, this is what we have. This equals this probability equals this probability, which equals this product of probabilities, which equals this number. And now in order to apply the remark, well, let's look at the sum over n of this probability. Sum over n, sum over n, sum over n. And here we get, well, this, what is this? This is a geometric series. This term here decreases to 0 exponentially fast. This is a number which is less than 1 to the power n. We know this is summable. So we can use the previous remark, which means we can use Borel Cantelli to conclude that this will not occur. So almost surely this will not occur infinitely often. And this is true for every epsilon. So now we can conclude through this rather abstract path that yn converges almost surely to 0 as n tends to infinity. This is much more abstract than what we did in the first video lecture of this unit, where the functions yn were described explicitly. So this function yn was described explicitly as really a function of some simple and very explicit probability space. Now here, this probability space, we don't say exactly what it is explicitly. It's just we assume there exists a probability space where we can define a sequence of independent random variables, each one with uniform distribution. So I'm not saying what this probability space is. It's certainly not the real line. It's certainly not the plane. It's more complicated. So we're just using these abstract tools and using the assumption that they are independent and that they have a certain distribution, we use Borel Cantelli lemma to conclude this convergence, this almost sure convergence to 0. Here's another example. I'm not going to make it explicit. It's just saying if we have a sequence of numbers that is increasing and another sequence of non-negative numbers that is decreasing to 0, but this decreasing is low enough so that it's not summable. Yeah, we know there are sequences that this decrease so slow that their sum is still infinite. Then, and if xn, I'm going to define xn as an independent, so here we're using dependence again, random variables with this distribution. Xn will be an with this small probability, and it will be 0 with what remains of probability. And well, what we claim here is xn, almost surely xn does not converge to 0. Okay, this is much stronger than the opposite of xn converges to 0 almost surely. So xn converges to 0 almost surely means the probability that xn converges to 0 as a sequence of numbers, this probability is 1. Yeah. So here the conclusion is that this number is not 1, but it's much worse than that. It is 0. Okay, so it does not converge almost surely to 0. However, it does converge in probability to 0 as n tend to infinity. And how can we prove that? Well, there are two things to prove. First, xn does not converge to 0. Okay, let's say almost surely xn does not converge to 0. And how can we prove that? We come here to this proposition of the last video lecture, and we see here how can we show that it does not converge? Well, for fn to converge to x, that will happen if for every epsilon to converge almost everywhere, that will happen if for every epsilon mu of fn is larger than epsilon infinitely often with 0 measure. And here what we have is the probability that xn is larger than, or take epsilon equal 1/2 infinitely often is 1 by Borel Cantelli lemma 2. So it is important then that they are independent because I'm using Borel Cantelli lemma 2. Okay? And why so? Well, an tends to infinity, so eventually an is larger than 1/2. And the probability that this event occurs infinitely often, it is 1 because they are independent, and the sum of their probabilities is infinite by assumption. Which assumption? This assumption here. Okay, so it does not converge to 0 almost surely. Now let's clean this mess and show that it does converge to 0 in probability. So how do we show xn converges to 0 in probability? Well, we just need to let epsilon be any positive number. The probability that xn minus 0 is larger than epsilon, it is exactly Pn, because xn is either 0 or an. And, well, it's at most Pn, because we don't want to consider the case when an may be smaller than epsilon for a few n's, but it's at most Pn, and, well, and this converges to 0 by assumption. It's again by assumption it does converge to 0. So, and that's all. This is the definition of convergence in probability and concludes the proof for this example. Here I would like to quickly highlight that in Borel Cantelli lemma 2, it is important that we check independence of the random variables. Okay, we just saw an example. Let's go back here where we saw that almost surely random variables did not converge by estimating the probability that they're larger than epsilon and showing that this is not summable. And here's an example. This was an example from the very beginning of this unit. Okay, that's a very explicit. Here's my space omega, is just the interval from 0 to 1. And I'm taking my random variable xn to be 1 on this set and 0 on this set. So this is saying the measure, if we take epsilon here equal 1/2, if we take epsilon equal 1/2, then this is saying the probability that xn minus 0, because we want it to converge to 0, that this is larger than 1/2. This is 1 over n. Or 1 over n is not summable. And if we do the same reasoning that we did in the previous example, to get this part here of the example, we would conclude that, well, then xn will be larger than 1/2 infinitely often, with probability 1. And then from there, we would conclude that xn does not converge to 0, almost surely. However, this is incorrect. We cannot, using the fact that it's not summable, conclude that something will happen infinitely often with probability 1, because we are using Borel Cantelli lemma 2 for a sequence of random variables without checking whether they are independent. And here, these random variables, it should be clear that they are not independent. And so we know they do converge almost everywhere. Why do they converge almost everywhere? Because they converge at every point except this one. So they do converge almost everywhere. This was the first example that we saw in this unit. It does converge almost everywhere, it does converge almost surely, even though this probability here, the sum of this probability will be the harmonic series. The harmonic series, we know it diverges. So we cannot make conclusions using Borel Cantelli lemma 2 without checking independence. And finally, to conclude this video lecture and conclude this unit, we're going to see a proposition. If the probability of an event occurring infinitely many times is 0, then necessarily the probability of these events, they have to tend to 0 as n tends to infinity. And the proof, let's see what the proof looks like. Well, if the probability that the events occur infinitely often equals 0, suppose this. So let's write bk to be the union of n larger than k of an, then we know bk is a non-increasing sequence of events, and it decreases to the event that an occurs infinitely often. Yeah, if we take the intersection here, it will be the intersection here, and this is just the definition of an occur infinitely often. As k tends to infinity, we have this convergence to this event here. But we know, so the probability of bk, it converges to probability that an occurs infinitely often, and we are assuming it is zero. By assumption, it is zero. Okay. But now, if probability of bk tends to zero, we just have to notice that bk contains ak, because it is the union of a bunch of events that starts at ak. Therefore, the probability of ak is bounded from above by the probability of bk, and because the probability of bk tends to zero, we can conclude that the probability of ak tends to zero, or the probability of an tends to zero as n tends to infinity. This concludes this video lecture and concludes this unit.